start new topic. So we'll be starting electromagnetism. Electromagnetism. So the topic is basically generation of magnetic field. So this is the topic. So how do you create the magnetic field? Just like electrostatic field, which is there surrounding a charge, there will be magnetic field surrounding a magnet, a bar magnet. So it's not only just bar magnet which generates magnetic field. There are other ways of generating magnetic field. So we are going to see the basic idea today, how to create magnetic field. So the core concept in this topic is as follows. A moving charge creates magnetic field. Okay, we know stationary charge creates electric field. Stationary charge creates electric field. Moving charge, of course, it creates electric field, it also creates magnetic field. But this charge should be moving with a constant velocity. Suppose if it starts accelerating, then it goes into a much more deeper concept where you get what is called electromagnetic wave. So basically, charge at rest creates electric field. Charge moving with constant velocity creates magnetic field. A charge which is accelerating creates electromagnetic waves in which the energy starts traveling as electric and magnetic fields in the space. So if charge is at rest, there will be electric field associated with the charge, attached to the charge. If the charge moves with constant velocity, there will be magnetic field associated with the charge, attached to the charge. But once the charge accelerates, there will be electric and magnetic fields dissociated from the charge and start propagating in space. So a moving charge, and here I'll put this restriction, moving with constant velocity. That is what we are going to look at. If it accelerates, then also there will be magnetic field, but it will be a dissociated magnetic field traveling in the form of electromagnetic wave. That we shall see later. So basically, a moving charge creates magnetic field. That's the core concept which we are going to deal with in this topic. So if you want to create a magnetic field, simple, take a charge, throw it with some constant velocity. It creates magnetic field. You also have the other concept, which is a current carrying wire creates magnetic field, because current carrying wire is nothing but collection of many moving charges. So I can go ahead and say current carrying wire creates magnetic field, and I use the symbol B to denote magnetic field with an arrow on the top, because field is a vector quantity. So why current carrying wire creates magnetic field? Because current carrying wire is collection of moving charges. So these charges are moving with drift velocity. These charges are moving with drift velocity, some Vd you can say, drift velocity Vd. So basically, it's at the end of the day moving charges, moving with a constant velocity, let us say, if the current is constant. So it creates a magnetic field. Of course, if the current is changing, then you will get again electromagnetic waves. It's possible to create electromagnetic waves if there is a changing current. If it changes in certain manner, there will be electromagnetic waves. So we are not going to focus on electromagnetic waves here. So our prime focus will be on generation of magnetic field using moving charge and current carrying wire. So that is going to be our prime focus. So prime focus, it's going to be on generation of magnetic field, which I call as B, by using charges moving with constant velocity, and wires carrying steady current. So either you can take a charge, but it should be moving with constant velocity, or you can take a wire which is carrying current, but current should be steady, fixed. So that is our prime focus. So why moving charge creates magnetic field? The answer we do not know. That's how nature works. Or why a current carrying wire creates magnetic field? We do not know. It simply creates. So we are going to study the working of nature by a law which we call as Biot-Savart's law. So central to this topic are following laws which we are going to study. Following laws. Law is working of nature. So law tells you how nature works. You cannot prove a law. You just only have to state a law. You cannot prove the working of nature. You just have to accept how nature works. So central to this topic are following laws. One is Biot-Savart law, which first we will study. The second is what is called Ampere's law, which we will study slightly later in the same topic. So these are the two laws, Biot-Savart law, B-I-O-T, Biot-Savart law, and Ampere's law. These are the two laws which we are going to study. So first we will start with Biot-Savart's law. So Biot-Savart's law gives you a mathematical expression to calculate magnetic field at a point due to a moving charge or due to a current carrying wire. So if I write here, Biot-Savart law gives us a mathematical expression for calculating magnetic field at a point either due to charge moving with constant velocity, or due to a steady current carrying wire. Okay, so let me write it properly. This is current. So that means Biot-Savart's law has got two variants. One variant is for a charge moving with constant velocity, and another variant is for a wire which is carrying a steady current. Okay, both these laws are interconvertible. If you know the law for a moving charge, from that I should be able to get the law for a current carrying wire, and vice versa also. If I know the law for a current carrying wire, I should be able to get the law for a moving charge. So let us see what this law states. Let us see that first, Biot-Savart's law. So that is our starting point. So law, as I said, cannot be derived, cannot be proved. It is just stated and you have to remember it. So suppose if I have a charge Q, okay, I am not putting any restriction on the type of charge. It could be positive or negative. Suppose this is going with a velocity v in certain direction, and I have a point which I am showing here with a red color, and my aim is to find magnetic field at that point shown by red color. So I want to find magnetic field at the red dot. Who is creating this magnetic field? This moving charge is creating magnetic field. So what you have to do first, from the charge you draw a position vector to that point where you are finding magnetic field. So I am showing that position vector here with a green colored arrow. This is my position vector R. So R is position vector from charge to the point where you are finding magnetic field. So R is position vector from charge to the point where you want to find magnetic field. Okay, so we have this R. So the law says magnetic field at that point P, I call that point P, So let me show it with red color only, because I have shown the dot with red. So the magnetic field at point P, now I am writing the law. So the magnetic field at point P is given by mu naught by 4 pi. You see, now we have got a constant which is similar to Coulomb's law. In Coulomb's law you had 1 by 4 pi epsilon naught. I have something similar here, mu naught by 4 pi, some constant. We will soon talk about this mu naught by 4 pi's value into Q. No doubt the magnetic field depends on the value of the charge. If the charge is more, the magnetic field has to be more. Into V cross R. So this V cross R is giving you the direction of magnetic field. So how to find the cross product direction? When you have two vectors, first you form the plane containing both vectors. First you join the vectors by tails actually. First you join the vectors by tails. You form a plane containing both the vectors. Put a screw at the point where tails are joined, perpendicular to the plane. If it is V cross R, rotate from V to R by smaller angle. See how the screw moves. If it is R cross V, you should rotate from R to V. Because here it is V cross R, you will rotate from V to R by smaller angle and see how the screw moves. So if you put a screw at the junction of V and R and rotate it from V to R by smaller angle, it is turning clockwise. So it goes into this board. So here V cross R is into the board. So that is the direction. So mu naught by 4 pi Q V cross R by R cube. This is the magnetic field at point P. Effectively, if you see, this law is inverse square law only. Inverse square law means it is proportional to R square. Immediately somebody will jump and say, sir, but you wrote R cube in the denominator. But there is another R in the numerator in the form of V cross R. So effectively it's an inverse square law. Okay, but to get the direction in a very convenient way, we are writing the numerator as a cross product V cross R. So Biot-Savart's law says, if there is a charge moving with velocity V, and if you want magnetic field at certain point, then it is given by mu naught by 4 pi, which is a constant, into Q, the charge value, into V cross R by R cube. So if the charge is at rest, if V is 0, then there will not be any magnetic field. So a stationary charge cannot create magnetic field. So from the law, you can bring out many interesting points here. So if V is 0, B will be 0. That's the first point. Similarly, if Q is 0, no charge, no magnetic field. So to create magnetic field, you need charges. Okay, compulsorily you need charges. Even if you take a bar magnet, inside that there will be electrons which are rotating, creating magnetic field. We'll talk about that later. So the basic entity required for you to create magnetic field is a charge, and that too a moving charge. Okay, now you should also note one thing here. If it is a positive charge, V cross R gives direction of magnetic field, V cross R. But if it is a negative charge, then when you substitute the charge value, you get a minus sign. So minus V cross R gives direction of magnetic field. So do V cross R and then reverse it if it is a negative charge. So the law is very deep. It is saying many things. So I will write the law once again here. Magnetic field at point P is given by mu naught by 4 pi Q V cross R by R cube. This mu naught by 4 pi is a constant whose value is 10 power minus 7. Very small value. You see, in electrostatics we had 1 by 4 pi epsilon naught whose value was 9 into 10 power 9, very huge value. But suddenly when you come to magnetism, the constant 1 by 4 pi, mu naught by 4 pi has got a very small value, 10 power minus 7. Here mu naught is called permeability of that medium. So it is telling you how much is the medium ready to allow magnetic lines to pass through it. Mu naught is permeability of vacuum here. If you write mu naught, it is vacuum. If you write mu, that will be permeability of medium. When you put the O symbol, mu naught, the 0 symbol, it is referring to vacuum. So mu is permeability of some medium. So if you are writing this law for a charge moving in certain medium, not vacuum, then instead of mu naught by 4 pi, you will write mu by 4 pi. Depending on the value of mu, the constant will have some value. But if it is vacuum, mu naught by 4 pi is 10 power minus 7. Then here I will write in green color, V cross R gives direction of magnetic field for positive charge. So V cross R gives direction of magnetic field for positive charge. For negative charge, minus V cross R will give direction of magnetic field. Because when the charge is negative, when you substitute the value of Q, you will put a minus sign there. So BP direction will be, magnetic field direction will be along minus V cross R. So for negative charge, direction of magnetic field is along minus V cross R. So the law is very deep. It is telling you that first the charge should be moving. If its velocity is 0, magnetic field is 0. Then the direction of magnetic field is given by V cross R. There is one speciality in this law. Let's look at that carefully. Suppose this is the charge moving with velocity V. Suppose you take the line along which charge is moving. This is the line along which charge is moving. Suppose if you take a point on that line somewhere. Suppose I took a point here called P and I want to find magnetic field there. Now the R vector is what you take from the charge to the point. So the R vector should be like this. That is our R vector. Now when you try to find the magnetic field at P due to this charge, you will write mu naught by 4 pi Q V cross R by R cube, no doubt. But here the V and R vector are parallel. So V parallel to R, because you are finding magnetic field at a point which is on the line coinciding with velocity vector, on the extension of the velocity vector. So V parallel to R, so V cross R will be 0 then. So very interesting point. If a charge is moving in certain direction, along the line of motion, magnetic field is 0 anywhere. Anywhere along the line of motion, magnetic field is 0. So for a moving charge along line of motion, magnetic field is 0 at any point along line of motion. At any point along line of motion, magnetic field will be 0. So this is important, okay, because the cross product will vanish. V is parallel to R and V cross R will be 0. So that means if I tell all this in a simple way, so if I have this charge moving with velocity V, except along the green line which I am drawing, except I am on the green line, at every other point there will be magnetic field. Only on the green line there won't be magnetic field. At every other point, for example, if I take a point here, there will be magnetic field. If I take a point here, there will be magnetic field. If I take a point here, there will be magnetic field. So at every point in space, this is a 3D. I am showing it on 2D, but you imagine it in 3D. So except along the line in which charge is moving, at every other point there will be a magnetic field. Okay. Now let us for a minute try to find the direction of magnetic field for some practice, because it's very important to find the direction of magnetic field. So suppose I have this charge Q moving with velocity V. So I am drawing the green line also, that is the line along which the charge is moving. To the right side of the line, if you take any point, for example, if I take a point here, to the right side of that green line and draw position vector, then V cross R, if you see carefully, it is into the board. So magnetic field to the right side of this green line will be in. I am assuming this is a positive charge. Okay. If it is negative charge, you have to reverse the direction of magnetic field. So here V cross R is pointing into the plane. So at any point on the right side of the green line, magnetic field is going to be the green dotted line, magnetic field is going to be inward. Whereas if you take any point on the left side, which I am showing with let us say purple color, suppose you take a point here and you draw its position vector r bar. Now v cross r bar, now it is outward. If you do cross product between v and r bar, it is outward. So here magnetic field will be out. So you see the way I am showing the direction of magnetic field. If I put a cross and a circle, this is into the board. Into the board. If you write this in your book, it will be into the page. If I put a circle with a dot, this is out of the board. So this is very convenient way of showing direction when you are working with 3D. So a circle with a cross means the direction is in. A circle with a dot means direction is outward. Okay, so this is the complete law which we call as Biot-Savart's law, but I have stated it for moving charge. This law can be modified for current carrying wire, or sometimes people first study the current carrying wire law and you can get the law for moving charge from that also. Okay, basically both are same, it's just two variants. So the person is same but he is coming in a different dress, it's like that. So the law is one only, but for moving charge it takes one form, it wears one dress. For current carrying wire it wears another dress. Now one thing you must keep in mind, very important thing, the Biot-Savart's law for moving charges can be applied if charge is not accelerating. If it is accelerating, you cannot apply it. You have to do something else. So please note here, I will write, this is a very important point. The Biot-Savart law for moving charges cannot be applied if charge is accelerating. It must be moving with constant velocity. Okay, this is very important restriction. We will see some problems where if you forget this statement, you will land into soup. You will have some problem. You will get wrong answer. So this is a very important point. So the Biot-Savart's law for moving charge cannot be applied if charge is accelerating. It must be moving with constant velocity. Same thing later we will even talk for current carrying wires. If it is a steady current, then we can give the law to find magnetic field. Now this law you cannot afford to forget it. So I am once again writing the law. Magnetic field is given by mu naught by 4 pi, whose value is 10 power minus 7 into Q. Obviously charge must come in the law. Without charge there is no magnetic field. Then the charge must be moving, so it must have velocity. So we write V cross R by R cube. Okay, by R cube. Let us see one small example. Suppose I have a charge Q moving with velocity V, and I have a point here at a distance R, and this angle is given to be 90 degrees. And this is the point where I am trying to find magnetic field. Find magnitude and direction of magnetic field at P, at point P. So let us see that. So we write B is vector form, we'll write mu naught by 4 pi Q. I am assuming this is positive charge. Let us say it is given as positive. Even if it is negative, I don't mind. When you substitute the value, Q will be negative and direction will automatically adjust. Q, V cross R. You see the angle between V and R vector is 90. So if you do cross product, it will be VR sin 90, that is VR sin 90 is 1 by R cube, that is the direction, sorry, that is the magnitude. Direction V cross R is into the board, so I'll write V cross R in. Okay, see R vector and V vector are joined by tails, form a plane containing them. put a screw at the junction perpendicular to the plane, rotate from V to R by smaller angle. So you are rotating the screw by smaller angle, means clockwise it goes into the plane. So this one R and this R cube will become R square. So the final answer is mu naught QV by 4 pi R square. So mu naught QV by 4 pi R square into the board directly, into the board. Suppose if it is a negative charge, you need not worry, because when you substitute the Q value, you will automatically put negative value. So you are getting a minus value in, that is a plus value out automatically. Minus value in is equivalent to plus value out. So you need not worry about the direction. Once you assume it positive and write it, it will work for negative charges also. You need not worry, because when you substitute the charge value, then you will substitute negative value obviously, and it will automatically take care. Okay, so this is Biot-Savart's law for moving charges. Now let us go to current carrying wires. So if I have Biot-Savart's law, Biot-Savart law for current carrying wires. So here I have a curved wire carrying some current I, and I want to find magnetic field at some point P. Now the problem is the point's distance from the wire is continuously changing. For example, the point's distance from here is this, from here is this, from here it's this. So the point's distance is continuously changing from the wire. So how will we write the law? So what we will do, we will take a small portion of this wire first, a small section of this wire. So I am going to take a small piece of the wire. Let us say here I will take that small piece, okay, and whose length is DL. So DL is the small length, small piece of the wire. DL is small portion. I shouldn't say small also. Infinitesimal is the correct word. Infinitesimal portion of wire. So let me not write small. Infinitesimal, infinitely small. So I took a small portion. I will treat this length as a vector. How? By giving the same direction as current. So I can put an arrow same direction as current and call it DL bar for convenience. So DL bar is a length vector having same direction as current, small vector tending to 0. Okay, from DL bar I will draw a position vector to my given point. So that will be the position vector to my given point. So first I will find magnetic field at P due to the current in DL bar. Due to the current flowing through this small piece of wire, I will find magnetic field at P. Then I will integrate if needed for the whole wire. So the law says magnetic field due to that small piece is given by, again, mu naught by 4 pi. Like previous case we have here also mu naught by 4 pi, because it is the same law but in a different dress. Instead of Q V cross R, here we have I, because there is current here, I. Instead of V cross R, here we have DL cross R by R cube. That is giving you magnetic field at P due to a small section of the wire of length DL, infinitesimal portion of the wire of length DL. Like this you find due to every small section the magnetic field, and then add it up vectorially. Finally, to get total magnetic field, add all the magnetic fields vectorially to get the total magnetic field. But I call this as the Biot-Savart's law. So Biot-Savart's law for current carrying wire is given for a small piece of the wire. For big pieces you have to integrate, but it is given for small piece. So this is what I call as Biot-Savart law for current carrying wire. Current carrying wire. Biot-Savart's law for current carrying wire. Okay, so this is a very, very important law. Now this law which I have written here, you can get it from the previous one which I gave for moving charges. You can get it from the previous law which I gave for moving charges. How? So let us look at that, how we can get this from that, how actually it is one law only but in two different forms. So let's try to see that. Let's try to look at that. Okay. So I'll erase this slide. Now, if I take a wire, so I will draw it in red color, this wire carrying current I, and we are taking a small piece of this wire like that, and it has same direction as the current, and I call it as dl vector, dl bar, and of course I am trying to find magnetic field at some point P, okay, which I am showing with purple line, and from the dl vector to the point P I have the position vector r, that is my position vector r. Now, what do you mean by current carrying wire? Actually, the electrons are drifting opposite to current, but for convenience let me assume positive charges are drifting in the direction of current. Nothing wrong. See, if electron moves from east to west, we say there is a current from west to east. Or if a positive charge moves from west to east, there is a current from west to east directly. So instead of saying electron moving opposite to current, there is nothing wrong in assuming positive charges are moving in the direction of current. In actuality, definitely electrons are only moving, but there is no harm in assuming positive charge is moving along the direction of current, because I want to work with positive charges. It's convenient. With electrons also you can work, but unnecessarily some negative sign keeps coming up and we have some confusion if we are not careful. So I'll work with positive charges. So this wire, obviously it's a metal wire, so let N be number of free charges. What are the free charges in the wire? Electrons only, but we can assume positive charges also for the sake of convenience, but actually it is electrons. Let N be number of free charges per unit volume in the wire. So if you remember, we have seen this quantity in the topic current electricity. When we were discussing Ohm's law, we derived I will be NEAVD, where VD is drift speed. The N there is exactly the N here. It is number of electrons per unit volume or number of free charges per unit volume. Means if this wire is made up of aluminium, for example, you take an aluminium block, you take 1 meter cube of aluminium block and see how many free electrons are available in that. That is N. Whatever is the metal, take 1 meter cube of that metal and see how many free charges are available. That is the value of N. So N is the number of free charges per unit volume. Unit means 1. Unity in English language means 1. Unit volume means 1 meter cube. We are taking meter as the standard unit. Okay, if you are working with CGS, unit volume will be 1 centimeter cube, but we are working with MKS system, so 1 meter cube. So NB is number of free charges per unit volume in the wire. Then volume of DL piece will be ADL, where A is area of cross section of wire, where A is area of cross section of wire. So A is area of cross section. So what is the number of free charges in the DL length? We got the volume ADL. In 1 meter cube, N charges are there. In ADL meter cube, how many charges are there? So in 1 meter cube, unit volume, there are N free charges. Whereas in ADL meter cube, how many free charges are there? So it is simply NADL. This is the number of free charges in DL length. This is number of free charges. You can say either electrons or even positive charges. If it is electron, the value is minus 1.6 into 10 power minus 19 is the charge of electron. If you assume it's a positive charge, it will be plus 1.6 into 10 power minus 19 coulombs. So this is number of free charges in DL length. This is the number of free charges, means 10, 20, some number. So total charge in this length, total charge in DL length will be NEADL. What is E here? 1.6 into 10 power minus 19. Suppose if you find 10 positive charges in length DL, each positive charge is E value 1.6 into 10 power minus 19. So 10 positive charges will be 10E. Here we have NADL positive charges. into E will be the total charge. So this is the charge Q moving in dl length with the drift speed Vd, because current is nothing but charges moving with the drift speed Vd, not the actual speed. The drifting is called current. Okay, normally in the wire also electrons will be moving randomly, but it doesn't give any current. But in the presence of electric field which is created by a cell, the electron starts moving along the length of the wire. So it is random motion plus regular motion superposed. So this regular motion is drift. Random motion is there, but this regular motion is drift. So these electrons are moving, or these positive charges are moving with drift speed Vd. So magnetic field at point P, I can write now, is given by, we are using the first form of Biot-Savart's law, mu naught by 4 pi QV, the V here is Vd, cross R by R cube. So I can write it as mu naught by 4 pi. Q we already got, the total charge, that is NEADL. So instead of Q I will put NEADL into Vd, the drift velocity with which these charges are moving. If it is positive charges, they are drifting in the direction of current. If it is negative charges, they are drifting opposite to the direction of current. Since we are working with positive charges, I will go this way, cross R by R cube. Now we can write this as mu naught by 4 pi NEADL Vd. I am writing Vd vector as magnitude plus some direction. What is the direction of this P vector? It is along current. Because Vd is along current, it is drift velocity of positive charges which are moving along current. So this P vector is along current, unit vector. So Vd vector, please note, this is very important. Vd vector I am writing as magnitude into some direction given by unit vector P. Okay, that's what I wrote. Now here, if you look carefully, NEA and Vd, that is exactly our current that is flowing in the wire. So I can write it as, I'll use the same color. So I can write it as mu naught by 4 pi. I am replacing NEAVD with I. The dl length scalar is there, that I will club with the P unit vector to make it dl bar, same direction as current, cross R, okay, and divided by R cube I forgot here. So here also divided by R cube. So you see I got this form of Biot-Savart's law from this form of Biot-Savart's law for moving charges. So I applied the moving charge Biot-Savart's law only. Okay, but in a wire, the Q value is NEADL. In a small length DL wire, the Q value is NEADL, and V is the drift speed of electrons, from which we got this. Okay, so both the laws are interconvertible. That's what I intended to say. So just give me 2 minutes, I'll be back. Okay, so now I have given you the proof how it is the same Biot-Savart's law but coming in different forms. Okay, so now we have to derive two important results using this Biot-Savart's law for current carrying wire. two important results with which you can solve almost 70% of the problems. So we'll have a small 5-minute break, then we'll continue this.